As we're getting started with Chapter 8, what I'd like to do is acknowledge that Chapter 8 does have a reputation for being one of the most difficult parts of the course. However, this only applies if people didn't understand Chapter 7 content. The reason for the Chapter 7 test is to make sure that you're well prepared for Chapter 8. Chapter 8 starts with us dealing with an acid-base equilibrium, as we have over here. We have Chapter 8 dealing with ice tables. We have Chapter 8 dealing with small x assumptions. We have Chapter 8 dealing with quadratics as well. Now, if all of those things make sense to you, well then, you can put a smile on your face because you're just fine. So sit back, relax, make sure you have a piece of paper. We'll see where you're at, and everything's going to be okay. Although you've already completed the acid-base introduction Edpuzzle video, what we have here is a quick rundown of acids and bases. The Arrhenius base contains hydroxide. The Arrhenius acid contains a proton. A Bronsted-Lowry base accepts a proton. We can look at nitrogen as being an example of this. In the case of ammonia, we have 3 hydrogens surrounding a nitrogen and a lone pair of electrons. This lone pair of electrons is able to reach out and grab onto that hydrogen. When this occurs, this here is considered a base, according to Bronsted-Lowry, because it accepts this proton. The fact that it reaches out and grabs onto the proton using its electrons doesn't matter here. We're looking at it as accepting a proton. In some cases, it has to rip it off of water. In other cases, it's freely available and it can grab it. This is labeled, though, a base because when this occurs, over here, we're left with hydroxide. So it creates a basic solution. Ammonia is a Bronsted-Lowry base. This is something that we see in Windex. So an active ingredient in Windex is ammonia, very small amount, and that's going to produce a small basic solution with hydroxide, and that's going to dissolve the grease and things on your window. If the question is, could I use oven cleaner or barbecue cleaner to do the same thing on my window? Yes, you could. It's about 10,000 times stronger than you need, so you'll just burn your fingers off instead. So use Windex because it has a very low concentration, but it's what you need to dissolve the amount of finger grease that is stuck on your windows. Lewis acid, electron pair acceptor. You'll see this more in biology. So a Lewis acid would be referred to as being this hydrogen here because it's accepting this pair of electrons. And this is the only time you're going to hear about Lewis acids. You won't see it on the test or anything like that. You will see it, though, in biology. We're going to take a closer look at water. One thing we haven't discussed with water is how water is in an equilibrium with itself. That does sound a little bit strange. However, water is able to break up into its own ions in a process called autoionization. When this occurs, we make an aqueous hydroxide and an aqueous proton. And I just said them backwards. Either way, an aqueous proton, aqueous hydroxide. We know that in reality, this proton is actually going to be H3O positive because it's stabilized by another water molecule to make a new molecule called hydronium. We'd write it as H plus aqueous just to keep things a little bit more simple. Now, this process here is very, very rare. It occurs really about 1 in a million times, but it occurs enough that it is significant because this means that pure water with a pH of 7 is going to have some protons, it is going to have some hydroxide. Well, that becomes hugely relevant because we can write an equilibrium expression here. Now, if you think about equilibrium, we've seen quite a few. We've seen KQ, we've seen QEQ, we've seen Q and KSP. We're going to compare this mostly to KSP, and the reason why is that we have a liquid on one side and aqueous on the other. The concentration of water within itself is meaningless. If you wanted to calculate the concentration of water, it's always going to be 55.55 moles per liter because in the liter you have that many moles of water. It's a grade 11 concept, so we'll leave that alone. But because the concentration of water is meaningless because concentration refers to something being in water, we leave that out. And we're going to leave that out to the point where we come up with a value called Kw, which is an equilibrium constant for water, and all that it does is it takes into account the concentration of protons and it takes into account the concentration of hydroxide. Dividing this by the concentration of water, or dividing everything by 55.5 moles per liter, would be entirely 100% pointless, so we don't do it. What we do, though, is we come up with this Kw expression, and this Kw is concentration of acid times concentration of hydroxide. And what they found out is that every single time this happens, that this has a specific value, and the specific value is 10 to negative 14. Again, thinking back to KSP, and if you're not sure what that is, pause the video for a second, go back to your notes that you've made on KSP. And for those of you that are a little bit confused here, yes, as I'm putting stuff on the screen, you should be pausing it, writing it down, looking at it, cross-reference with your textbook. Really force yourself to engage. Without that, it's me talking at a screen and you looking at a screen, and not a lot of benefit. So you need to be writing this down, thinking about it. If you get stuck on it, look it up somewhere. Or email me, that's good too. So if you look back to KSP, we could solve for either of these concentrations by taking the square root. We could make a nice table and blah, 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 and we'll do all that stuff again. But really quickly, just by taking the square root, because we know that that concentration and that concentration are the same, therefore we can take this concentration, what we end up finding is that X equals 1 times 10 to negative 7. This is not a coincidence. This is mathemagical. This is wonderful. And the reason why is we have a negative 7 here. We have a pH of 7 over here. There is a reason why the pH scale goes at has 7 being neutral, because that is the concentration of protons at a neutral place. It's a concentration of hydroxide as well. So the pH scale, not a coincidence. Now the follow-up part of this are the two equations we've seen before in grade 11. Those equations are pH is the negative log of the proton concentration, or the concentration of protons is 10 to the negative pH. If you're wondering why my handwriting is terrible, it's because I'm using a tablet. I don't want to spend $1,500 on an iPad Pro, which apparently is awesome. Anyways, so we have these two different equations here. They still apply, and we still have our concentrations here that now relate to Kw. I would suggest somewhere that you make a review sheet or summary sheet or a cheat sheet, if you want to call it that has all our different K expressions on it and ties them all together. Because this Kw should look exactly like KSP. Maybe even make an arrow going from KSP to Kw to show how you're really dealing with the same thing here. So take a minute and do that. Once you've done that, what I'd like you to do is take a look at your textbook and look at weak acid dissociation. Weak acid dissociation is a simple formula. It talks about percent ionization. You can look at that in your textbook. You'll have no trouble dealing with that yourself. Work through the blue example, and you're fine. Our next step now is to look at Ka and Kv. So now that you've updated your notes to include the percent ionization equation, what we're going to look at is our specific example from before, where we had acetic acid, and we used this equation here. You might have recognized this or seen this on your quiz or anywhere else. Now, this is the same equation we've had, whereas we have the acetic acid molecule with its covalent bond. Water's ripping off a hydrogen. It makes hydronium, H3O+, and the acetate ion with a negative charge. So everything so far is exactly the same. Previously in the notes, what we said we could do is we could write a KQ expression, products over reactants. We're going to do that. KEQ equals our concentration of acetate. I'm going to simplify acetate just to AC negative, and hydronium to H+. We do know it's H3O positive. We're not writing that because it's easier to write it this way. Scientists are efficient in that respect. If you had to pick between H+ and H3O, you're going to pick the H3O because that's actually what's going on. On the reactant side, we have HAC, or the protonated acetate. ion, protonated acetate ion. Now, I remember in first year in grade 12 chem being so confused how H plus, a proton, and hydronium were all used interchangeably, and I couldn't figure out what was what. Well, H plus is a hydrogen atom without an electron. Well, if you take away the electron from hydrogen, you're just left with a proton. And hydronium again refers to this H3O, which is the proper way to describe that. Now, I'm going to delete this, otherwise someone in the future will see this and they'll wonder what it is because they didn't watch the video. So, we have KEQ, our acetate ion, and our proton as over our protonated acetate. Now, we could call this KEQ, which is 100% correct. However, to be more specific, and thinking back to even to grade 10 literacy, one of the key things that you learned is that being specific, adding those details, makes your work clearer. So we're going to call this Ka instead of KQ. The only difference here is that we're recognizing it's an acid and we're discussing it in this portion. There's no other change to this whatsoever. It's just KQ of an acid. And instead of saying KEQ of an acid, we're going to write Ka. The second part of this refers to Kb. So Kb refers to the formation of a base, but it's not quite what we would have expected. And this is why. Muy importante. So first of all, we need to acknowledge that this is the forward reaction, and the reverse reaction would be these two things flipped over. However, this isn't considered the basic reaction. It's considered the reverse reaction. The basic reaction takes our acetate ion that's formed, and then it's going to have this acetate ion interact with water. In the previous example, the acetate ion interacted with existing acid. It would if that's present, but if that acid isn't present and all we have is this acetate, I should include a negative charge here to be complete, this acetate will interact with water. Rarely, but it will. So those electrons reach out and they grab a proton. The electrons here head back to hydroxide, or the oxygen, to make hydroxide. Well, why is this happening? Well, because electrons attract things that are positive. They're negative, they attract something that's positive. This plus here is not a positive charge on the proton. It kind of looks like that now, so we'll get rid of that. It's really just the hydrogen. So the negative attracts the partially positive on the hydrogen here, which isn't shown. When this happens, what we end up doing is we end up forming two things. We end up forming our acetate ion as we had before. So our HAC is formed. And we also end up forming the other thing, which is, you're thinking it, I know, hydroxide. That means that we now have a situation where our acetate is acting like, let me zoom out, not working. All right, we have a situation where acetate is acting like a base. And it's acting like a base because we have the acetate ripping off a hydrogen and creating hydroxide. This is where the Kb expression comes from. So our Kb is going to be an equilibrium expression like we saw before. It's still going to be products divided by reactants, still leaving out water because the concentration of water is meaningless, over our reactant, which is our acetate. So if these equations are correct, they should be able to tell us something more. Well, let's see exactly what we're dealing with here, knowing that this acetate regenerates the acetic acid that we started with in the first place. There should be some connection between Ka and Kb. So let's see exactly what this gets us. We'll multiply them together and see where that leads. Again, in your notes, you should definitely be doing this as well. So we're going to get a nice black pen, and start on our way. So we know that Kw equals the concentration of protons and the concentration of hydroxide. Therefore, we should be able to take these pieces here and do something with them. So let's try that. I'm going to take the values given here from our previous equation and substitute it in. We'll start with this one over here because it's readily available. And I'll put little times in the middle here just to keep them distinct. So this hydroxide is substituted in. If I'm substituting this in, that means I would have Kb times AC, should use square brackets, divided by HAC. So again, so I've taken this, I moved that over there, divided both sides by AC in order to get this expression right here. I can do the same thing with our Ka value, which is up here. I'm going to have Ka times HAC divided by AC. Ka times the concentration of HAC, all divided by the acetate ion. If you're looking at this and you're having another mathematical moment, you are fantastic, because this should make you super happy, because by looking at this, what we see is that acetates on the top and bottom, and they cancel out. Acetic acid, top and bottom, they cancel out. And what we end up with then is Kw being Ka times Kb. Therefore, Ka times Kb also equals 1 times 10 to the negative 14, because that was the numerical value of Kw. So right now we have a whole lot of stuff that all is the same thing. So Kw equals Ka times Kb equals 1 times 10 to the negative 14. So if that's okay so far, then what I'd like you to do is try writing your own K expression for ammonia in water. You want to compare the Ka to the Kb value by multiplying them as we did above. A whole lot of stuff should cancel out, and you should essentially prove that Kw equals proton concentration times hydroxide concentration. When you're done, look at the answer.